Yeah, hello. I'm PC from Scopex, and I'm specialized in 4K coding with assembly language. And today I'm going to talk about how to get rid of the exe header under Windows, or in other words, how to get a real Windows 32-bit callback from a COM file. Parts of the presentation are going to be very technical, so to follow those instructions you need the knowledge of Windows 32-bit assembly programming, as well as some system internals, plus how old 16-bit COM files work. Okay, this is a short overview of the presentation. I will start with the motivation. It should be more or less obvious why you want to get rid of the exe header. Then I will talk how I found a working solution that was not easy, and I will go into details, show some code parts, how this works internally, and at the end I will talk about the pros and the cons of this technique, and at the end we will have some questions. Hopefully I can answer them. Well, first of all, is the exe header really that big? There are several common workarounds, like putting data into unused parts so that you don't waste that much space. Or another used technique is to make the sections in the exe header overlapping. But with both versions I had massive problems with compatibility issues, so it does work to some extent. Well, yeah, and you could also leave out the last padding of the last section. And okay, you're going to compress the exe file anyways. Two common methods there are to embed the exe file into a COM file, and where the COM file just extracts the exe file to a file and then executes it. And the second common used method is to use a Windows cat packer and put everything into a batch file. But both methods still need to create a temporary file, and I'm not happy with that solution. So I was seeking for a stable solution which works on all common Windows systems, and that I don't need to worry about the access header structure and how to rearrange things and worry about future systems, and that it works. And I also wanted to have a more general solution, because it was always a pain in the ass at the end to search for data which fit into those sections, and then I also needed to enhance the code to address those things. That was really a pain. And what I want is a way for just executing the file. No temporary files created on your disk, just execute, so that you could even execute it directly from a read-only device. The smallest size I could get was about 360 bytes. Some of you might get it smaller, I don't know, but I don't need it anymore. Well, as I said, the common workarounds have disadvantages, and the big thing is there is no way to execute or to write 256-byte intros for Windows, because when already the exe header is bigger than this size limit, it's just not possible. And well, the only thing, the only way to execute real Windows 32-bit code is via a valid exe header. So everything else is impossible. Is it really impossible? Well, you need to know more about what's going on behind, how Windows manages those 16-bit COM files. And, well, basically, this is done via the so-called NT-VDM, the NT virtual DOS machine. Each DOS application, each COM file gets its own environment. And this is basically a kind of emulator where everything is virtual. And there is basically no chance to get out of this virtual environment to some extent. So one of my first approaches was to look at the interrupt table. There are tons of interrupts for the DOS interrupts documented, and there are even some with Windows extensions. So I spent a couple of days to look into those interrupts to just find out that most interesting one, which could provide a Windows 32-bit callback, do not work under Windows NT 2000 or XP. They are just used for Windows 98 Millennium Edition. So only a few of the big interrupts are available under Windows NT 2000 and XP, and none of those interrupts that are available do a direct Windows 32-bit code call directly. So this is because the virtual DOS machine emulates basically everything. So this was just not possible with interrupts. The second approach was looking at the VDD interface. VDD means virtual DOS device interface, and it's basically a backdoor from Microsoft, so that this virtual DOS machine can be enhanced, and that people can write their own drivers to get all the programs running under this environment. Unluckily, this is not well documented, especially in the current documentation. So it took me a time to get an old NT 4 point whatever DDK, and there it is really good documented. So with that I could work. And well, the basic idea is behind that is that there are special invalid opcodes which are interpreted by this virtual machine to trigger calls to a Windows DLL. So this is the interface we are interested in detail. Basically, it consists of 3 calls. The register call on the right side. Here you see the special opcode for those 3. The register module basically loads a DLL. You have to provide the name of the DLL. You have to provide the name of the initialization function optionally, and you have to provide a name of the dispatch routine. It returns the handle if it was successful, or an error code if it was not successful, depending on the carry flag. So basically, it works like that in your 16-bit environment, you do the register module, which internally uses the load library and calls the init function in the Windows 32-bit DLL. Then you do the dispatch calls, which do a real Windows 32-bit call in the DLL, and at the end you have to unregister it. Well, this is the interface, how it was supposed and how it was designed. But this interface has its limitations. It, of course, makes it possible to call 32-bit code from the virtual environment. But the DLL still needs a valid exe header. And even more worse, you now need two files, the COM file where you trigger the call and plus the DLL. And this is basically not what we want. We want one file, one call. So I had to think of how to abuse this interface to get what I want. And yeah, I was thinking basically of using standard DLLs which are available on all Windows systems and try to somehow hack them via buffer overflow, stack corruption, or use kind of callback functions. There are several functions in standard DLLs available. For example, when you create a window, you can give a function pointer to a get window, a window callback function. So if I could use that to get a callback, this will work out. So I had a look at the available standard DLLs, and I wanted to get it work for all Windows versions. I also, for that, I need to know how this really works in detail, how the stack looks like when the register module or the dispatch call are done. And I also needed to find out any functions which provide a callback, which are unluckily not that much, and especially it needs to provide the parameter on the function list exactly at the position I needed it. And yeah, this is gonna be a challenge. So the next step was just to write a small test DLL and to see how this really works out. For that, I made my DLL and I implemented a breakpoint, a compiled breakpoint, which basically is just an interrupt free. And on the other side, I made my COM file where I did the register module and the dispatch call. And then the DLL was loaded up, it was called, the breakpoint hit, and the debugger came up, and I could explore the environment. So what things I've seen from that? Well, basically first I saw the stack and also the call stack. I've seen that the call comes directly from the NTVDM environment, so that there is no fancy handling with threading and that stuff. It comes directly through. I also had a look at the registers. Unluckily, none of the registers could be used. None of them had the same content as on the 16-bit side, because they're just virtual in the emulator. And also no register pointed to the COM file. So the registers are more or less useless. But what really helped was that I found out that the memory maps one by one. So if you remember on the DOS times, you build an address by taking the segment, shifting it by 4 to the left, and adding the offset. And with that address, you have the same address basically in a 32-bit environment as well. So that makes the hack or this even work basically. And yeah, one additional thing I found out that it is handy to have a 16-bit debugger. I would even say it's necessary to find things out and also to use this. So, okay, the first thing was that I looked at the stack, and as the dispatch call, the function in the DLL has per definition no parameter, I tried to mess up the stack by using a function which had or would take parameters to mess up the stack and to kind of get a callback. And unluckily, this does not work because most of the DLLs, basically all I had a look at, were written in C, and they had a different calling convention where they saved the stack before, so this is just not possible. And well, the second thing, I was searching for functions in standard DLLs which provide a callback, like the create window, and basically it's hard to find such functions. Second, it's hard to then find out how to trigger the callback, and third, it had to fit to that stack. So basically I found 3 or 4 functions, and they all did not fit the needs. So this was again the second point where I thought, okay, it might really be impossible. But I didn't give up, and I started to dig even deeper into the NTVDM and kind of debugged those calls and had really analyzed the code, what they did. And yeah, as I said, here I had to use a 16-bit debugger plus a 32-bit debugger together. So what I was doing, I took the 60-bit debugger in the COM file, loaded up the COM file. So this guaranteed me that the virtual DOS machine was running, and I could attach the 32-bit debugger to that machine. And then I executed the 60-bit program, and well, and then was able to step through the 32-bit parts of the NTVDM and kind of analyzed the routines. And yeah, basically I was searching for possible bugs, like did they really handle all the error cases, like what did they do if the DLL did not exist, or if the DLL was invalid? Would it crash, or I mean, would it help me to get a callback? What will happen if the init function does not exist? What will happen if the call function does not exist? And I also found out while debugging that stuff that there is a maximum of 9 possible loaded DLLs. So you can have maximum 9. And I tried what happened if you load more than 9, and if the handle you provided was just bigger than 9 or 0, and they all handled the cases. So this code really seemed to be stable. But luckily I found a bug. What they did not think was that a stupid programmer could call the dispatch call before using register module. And wrong direction. So what happens? As I said, there is no check if a DLL was registered before. And second, the address, the NTVDM has a lookup table for each of the 9 possible loaded DLLs. And this lookup table is initialized with 0. And the third necessary point is that due to the fact that the memory maps 1 by 1, address 0 is a valid address. because on the DOS machine you have on address 0 the interrupt table. And yeah, well, this makes it possible. So all we need to do is get sure that on address 0 there is a valid opcode. Basically what I tried first was move the whole intro to address 0. But luckily this didn't work out because of the emulation, and there are weird things going on. Like I think that it was a timer interrupt or something that messes it up. But it's enough to provide, for example, a jump. And yeah, well, so all you need to do is get sure that there is a valid code on address 0, like the jump to your 32-bit code. And then do the dispatch call with an uninitialized handle between 1 and 9. And voila. You will get a call, a real Windows 32-bit call from your COM file. So here is the code in detail. What I do here, oops. Basically, well, first I set the extra segment and the destination register to 0. Then I move the opcode for the jump. This is E9 to that address. Then I calculate the current address, or the address where the jump should go to. In this case, it is the entry point for the 32-bit part. Because the jump addresses are relative to the next instruction, I need to subtract 5 from that, because 5 is the size of the jump command itself. Well, basically then I move the address to the opcode and get sure that AX, the handle for the dispatch call, is initialized with 1. And as I did no register before, this dispatch call will give me a call to address 0, which then calls the entry point. And that's it, how it works. But this is just half of the story. Because, okay, now we are in 32-bit, but we can't do anything, because there is a reason why Microsoft invented the exe header, because it loads up the DLLs you need automatically. So you have to do this by hand. And even more worse, the functions for loading DLLs are also in a DLL. So, well, one thing you could do is, like what people do in virus coding, is scan the memory to find the kernel 32 DLL, which provides then the necessary functions like load DLL and get proc address to load up other DLLs. Or second, even more easy, but not that compatible, is as the anti-VDM already uses DLLs and also uses the kernel 32. Of course, at least it uses it for the register module function. So the anti-VDM knows the kernel 32 and knows the load library, and you can directly hook into that. But as I said, this is not that compatible. So then you need different versions for the service pack 1 and 2. And yeah, the next big problem is that COM files can theoretically be on any 16-bit aligned address within the DOS environment. And I was first thinking that due to the reason that every time a new instance is started, it will get the same address, but that's wrong. So, well, and the fact that most of the Windows intro code relies on existing structures with fixed addresses, this is going to be a problem, especially if you use higher language code. Well, so to work around this, you can either use relative code, which I would not do, and it is really, with the internet instruction set, this is really hard to some extent. You could copy the 32-bit part to a fixed address, which is basically what I use most of the time. Or you could change the code a bit that you don't do the jump directly. Instead of that, you could write the address to a register and then jump to that register and use that register as kind of base address and use it to address the data. So, okay, these are the problems with that. It is really hard to debug. I wouldn't write it from scratch. What I do is, I most of the time have several different configurations in my intro. So I start with just using the good old exe file, where I can step through and debug. Once this is working, I just change the configuration to use a trick, and if it then crashes, it's really complicated to find the bug. But it can crash, because although I get a complete Windows 32 call, the environment is a bit different, because the registers are set up differently on startup, and your code is basically still running under the process of the NTVDM. So if there is a bug, you need a 16-bit debugger and a 32-bit debugger, and like I found this out, you need to first load the COM file into the 16-bit debugger, then attach with a 32-bit debugger to the NTVDM, set up your breakpoints, and then you can run it from the 16-bit debugger side. And yeah, this is really complicated. The next big thing is, I'm not sure about newer Windows versions, especially 64-bit Windows. I've heard that they don't support the DOS part anymore, so it might be that it doesn't work with the newer versions. And many people are now writing their intros in higher level language like C, C++, and this will be not easy to use with that trick. But it is very stable. It worked on every NT Windows 2000 and XP system I tested it. When it crashed, it was most of the time because I had a bug in finding the kernel 32 DLL, or I had a problem with different ordinals, all that stuff. But the call is, as I say, it is stable and it works. It works even better as the exe file. When they change to Service Pack 2, you sometimes get, when you execute an exe file, you get a warning that this file isn't signed and may be unsecure. If you use that trick, you don't get that. And even better, you can do a return, and it cleanly returns back to 16-bit. So what you could do is, in theory, split up your code and do things which are smaller on 16-bit on the 16-bit DOS side, and the rest on the 32-bit. Yeah, as I said, it works on all the tested versions. And one additional nice thing is that it makes it possible to write 256-byte intros on Windows, and not just DOS-like. And yeah, well, and then I just use APAC to pack it, and it runs perfectly. I was also thinking this might be a future extension to use a cabinet DLL directly, but for now APAC is okay. So before I start with the questions, I can show you one thing I had for the function party 2005. This was basically 3 days before I found that bug, and I was sitting at the party and was thinking, yeah, it might be cool to have something in 255 bytes. And as you see, the size and this. Oops. Okay. Yeah, that's the first time. And it even worked before.
Welcome to Function 2004.
The monitor takes up some. The beamer takes some time, or it seems that it has a problem. Yeah, basically what you would have seen is a simple fractal.
Maybe you can show us the laptop.
Ah, okay. Yeah, that's a good. I think it has to do. It's definitely working. I think it has to do with the graphics driver and the way I use it when it's connected to the beamer. So when I do it locally, it works, and it worked before. So when I plug it out.
Welcome to Function 2004.
So, can everyone see it? Yeah. Okay. So, if you're interested, I can show bits of the code. Yeah, basically, here is the trick. I get a call to the 32-bit part. That's here, where I do some fancy stuff. Basically, load the library I need for the Windows synth. Then what? Yeah. That's basically what I said before. That you can either scan for the kernel 32 or direct hook into the NTVDM. That's how it works. Well, these are the IDs for the call. You see a nice compression, because I was already at the limit, so I had, for example, to get rid of some letters, and it still sounds good. And then the nice thing is here, I do a read, and I get back where I was calling from. So after the read, it continues there by initializing the graphic and do the rest. Okay, are there any questions?
Yeah, I have a question about the memory mapping. I didn't get that. Where the 16-bit memory gets mapped to on the 32-bit environment?
It maps one by one.
Yeah, but where? Zero. Starting with zero?
Yeah.
Zero. Virtual address space.
Yeah.
You said with the VDD you can, as far as I understood, load every library and call every function from DOS.
Yeah, to some extent. So, okay.
My question would be, could you write DOS into using libgl calls?
Yeah, that is what the main idea behind that interface was. When
you don't have any Windows code, but just DOS code, but call Windows libraries. Would
Yeah,
that be
yeah,
possible?
yeah.
Of course.
I've seen a code where a guy was writing his own virtual video driver by using DirectX with that technique, so that he could run DOS games with DirectX support. Yeah, basically all you need to do is hook up and to the with that to the VESA interrupt, and then just copy over the buffer for DirectX, or you could even use the same memory to some extent.
What is when you need more than 1 meg of space? Use the stack on the
Well,
bit side, or how much is there available?
yeah, basically as you get the code from the NTVDM, you are limited to the stack sizes defined there.
Okay, how big it is?
I think the standard is 64K, but what you can do is just an allocation. It's a call. Okay? No questions? Okay, thanks.